好，我们开始上课。那么今天的课还有30号，是后天还有课。我最近上课上的很频繁，希望大家能及时的消化今天的课能够留一点时间的话，解决大家一些问题。Let me remind you last week. We just learned how to quantize free fields. Free is very simple, but quite unique. What we need for harmonic oscillators. And the result is also very simple. Basically, we have a harmonic oscillator for each. And then we sum over the p. Then we get the quantized free field. So in this quantized free field framework, we also decide how to find the particle state. So to find a single particle state, the two particle states, any particle state on the whole space. Since this is a free field, you don't touch it. So we also mentioned some conserved current, conserved charge, how to understand the conserved charge, play the role of the generators, meaning they just generate the symmetry transformation. For example, Hamiltonian generated the time evolution, moment generated the space translation. And there's a very universal feature for those conserved charge. So basically, for any continuous symmetry, there is such a U operator, which is defined as U operator, which is defined as I alpha Q, the Q is essentially. So we're learning from mechanics, this U operator implement symmetry transformation. Okay, whatever symmetry it is. If you give me a state, I want to transform the state, then I actually see U operator on this state. Okay. If you give me an operator, I want to transform the operator. Yeah, I just acted by U dagger U. And the operator is inserted in this U dagger U. So, as we mentioned at some point, we wanted to understand how the operator by X acts as a vacuum, as we discussed last time. This is not quite the same as the position eigenstate operator. Let's state position eigenstate in quantum mechanics, right? Even though it looks like there are local excitations. The one key evidence is if you try to think about the overlap of that kind of state with the other state located at y, then the overlap is not zero. Okay, but we learning quantum mechanics because the position eigenstate, you have to orthogonal to each other as x and y. Don't have any overlap. So we're going to see this more precisely. Okay. How to calculate the overlap of this kind of state. Okay. So as you can see, this is nothing about you consider 2 phi. Okay, the expectation value of 2 phi. Right. You consider one phi. You can also consider 2 phi located at different positions. So sometimes this is also for the 2-point function or 2-point correlation function. So 2-point function. Simply termed as 2-point functions sometimes short. So how to calculate this one? How to calculate this one? Well, as learned last time, the stupid way is just insert the operator definition of this phi. Okay, just plug in the definition operator definition of phi in terms of A and A dagger, and plug in the calculate. Okay, that's the thing you can do. Right, and this phi, the sum of A dagger, T dagger, and as you can imagine, some terms give the trivial result because whenever it's A acting this vacuum, then clear the vacuum, you get 0. Okay, but there are some terms left. Some terms, which kind of term? Some terms looks like AP, AQ dagger. This kind of terms, right? You can check. Then you use the commutator of A dagger in order to compute this one. Use the commutator, then you will get some number. Okay. Here's some number. Essentially, because of this term is not trivial, this is actually per function d minus 2. Then you can calculate this one after the final integration over the momentum. Then you get the result. So let's try to do it. So let's below the 2-point function. Label this 2-point function as a d. Yeah, as a d. You just label 2-point function, and of course, the eventual function you will get will be a function of x and y. Okay, or x and y. You see. Now, because of translation symmetry, it actually can only depend on x minus y, distance. See? There's a translation variance. Okay? Translation variance. Well, let's denote this 2-point function using dx minus y and dx minus y will be equal to eventually, after you plug in the operator definition of phi, and using the commutators, using the commutator relations, and what you obtain is something like this. Okay. You can justify yourself immediately. This will be the result. Because there function carries one's momentum integral. Okay, but there are two. Okay, there are two phi insertions. Each phi carries a momentum integral. All right. The two independent momentum integrals, and the delta function carries once, and there's one more left, which is the eventual p integral here. You see? And this comes back to last time big question. Where can we see the Lorentz invariance about this 1 minus square root of 2 omega over? In this case, it's essentially 1 over 2 omega, because you have 2 phi, right? Now here we can see the Lorentz invariance clearly. So this part is Lorentz. Let's prove. And this is of course Lorentz invariant, because this is inner product for vectors, you see? Okay? So this means the two-point function, you can view this as some observable, okay? For observable, you can talk about Lorentz invariance, okay? Indeed, the result tells this is Lorentz invariant. This is both two parts are Lorentz invariant. Once you have something, okay, well, if you like it, then you can compute this integral further, okay? Compute it. Maybe you can try for a few seconds how to compute this integral. This integral is a three-dimensional integral. The point you have to keep in mind is omega p, or this p0 is not independent of p, okay? Okay? So this is a very defined three-dimensional integral. Because you should be able to compute it. So, but it's not trivial. You can try for a few seconds. Or you can plug into Mathematica, see what it takes. Do you know how to use Mathematica? Mathematica didn't do integral, right? You let the Mathematica do the integral for you. It's not trivial. It's highly non-trivial integral. Okay. It's very defined. And yeah, it's simplified. But one advantage, before we explicitly compute this integral, at least we know this integral is very manifestly Lorentz invariant. Okay. If you have something to compute, but you know this is Lorentz invariant, you can do a lot of things, right? If you understand what do we mean by Lorentz invariance? Lorentz invariance is really a powerful symmetry. Okay. See? Lorentz invariance means it doesn't matter you do in which frame, okay? Then you can choose whatever frame you like. You can get the same result, okay? That means Lorentz invariant. If the integral is Lorentz invariant, then you can choose whatever frame you like, okay? Okay? The point is, if the frame is Lorentz transform related to other one, your single choice and the calculation is enough to cover all the related frames. But provided those frames are connected. So because of that, let's try to do some simple analysis how to deal with this integral. So since this is a Lorentz invariant set, do a lot of things. We discuss separately x and y space-like or time-like, okay, or time-like, because as we learned in the first lecture, if it's space-like, it cannot be rotated to time-like. Okay, if it's time-like, it cannot be rotated to space-like. We have to discuss separately. Okay. So if x, y are time-like, and instead we can choose whatever frame we like, then we can choose a very simplest time-like frame. What is that frame? Okay, what is the simplest time-like frame? Just view x and y are the two time coordinates, right? Nothing else. Okay, that's the simplest time-like frame, which means x the 0 minus y0 t, and all these instants are turned off or 0. Okay. This is my simplest time-like frame. Simplest time-like frame. Okay. This essentially means that this is my time direction, and x and y is in, yeah. This is my x and this is my y. Okay. We share the same position, but only time coordinates. Okay. Then of course the integral will be simplified, right? This is a three-dimensional integral. The integral will be simple. In this case, so dx minus y will be given by, you can check. Can we buy this one? Check. Okay. Easily check this out. This is only one. There's only one component. Set the p is equals to p. The p is equal to p0 p vector. Okay, and this is not independent. This is omega p. Okay. Okay. Now omega p is defined as vector squared plus the squared. When I turn this three vector p to the normal p, this p is actually normal p. Okay, then I append this integral. It's still not trivial, right? This integral. Other than this integral, not trivial. And it is. Well, we observed that there are some common factors that look like this, right? It may motivate you to do some variable, change variables. You see? I can do change variables. I can send this square root as some new variables. Is that right? So yes, that's correct idea. So if you do this change variables, for example, I denote this square root as capital E as my new variable, then this integral returns to this one. It's a little simple, but it's still an integral. At least in this case, maybe mathematically can help you to do. Someone you can do it straightforward. So this integral, the behavior, the simple behavior when t goes to infinity, t is here. If it goes to infinity, this integral goes like e minus t. Okay. This is a simple behavior of this integral. Of course, the full result of this integral is still highly non-trivial. But when t is infinitely large, when t is infinitely large, means what? Means x, y are infinitely separated. The t is the time coordinate distance between x and y, which is when x and y are very far separated from each other, only in time direction. Then this integral goes to e to the minus 9mt. Okay? There are a few messages maybe important. First of all, this is a complex number. Okay. This is a complex number. It means when you want to compute 2-point function, you shouldn't think that you shouldn't think you always get something real. Okay. You see? Yeah, if you like it, you can use mathematics to plot it, and you can get more complicated behavior. For finite t, both the real part and the imaginary part, okay, with this 2-point function. So that's one try, but this is only the case for inside the timeline. Okay. And separately, you should also consider they are space-like. What if x and y are space-like? Okay. As said, we should discuss this case separately because you can never rotate. I mean Lorentzian rotation. Okay. Or Lorentz transformation. You can never rotate from a timeline to space-like. So they are not connected to each other. Okay. So if they are space-like, you have to choose another frame, right? Choose another frame. This time, I will turn the distance in time coordinate to 0. Okay, because I want space-like. It's simply the space-like. I don't want to bother myself to go complicated or general case. It's not needed. Okay. I want to make use of this Lorentz invariance. Okay, simply my problem. So in this case, I can consider only their space distance in x and y. For example, the space distance is given by r vector. R vector. Okay. This means that if this is my direction, then this will be my x and this will be my y. They only separated in space, and since I have 3-dimensional space, there's no the vector. Okay. Now what happens for my integral? Then my integral becomes a little simpler. And this one, right? Instead of 4 inner products, now I only have 3 vector inner products. Because t is 0. Because t is 0. Now, again, this is non-trivial integral. And calculate it after a few steps. You realize that with the one message, you can justify yourself. This is not 0. This is not 0. This is not 0 justified what we claimed the last time. The overlap is not 0. Okay, so in both cases not 0. But this is a little more interesting, right? This is a little more interesting. Think about yourself. What we're doing. We're not claiming that even the two operators, two fields, are space-like. Okay, space-like. Physically, you might think, okay, maybe these two guys are nothing to do with each other. They don't talk at all. But in this case, the overlap is still not 0. Okay, overlap is still not 0. This is acceptable, right? This is okay, right? This essentially means consider this as an overlap. This essentially means, come back to here, essentially means this state and this state, okay? There are two states. Now we're talking about the overlap. The point is, even these two states located at space-like a separate point, they could have a non-trivial overlap. Okay, this overlap doesn't have any meaning of communication. Okay, Okay, in spatial relativity, what we learned is if the space-like, we cannot talk. That's true, not communicate. But this is nothing to do with communicate. It's just the overlap. Because you this side you have a highly non-trivial wave function. This side you have a highly non-trivial wave function, right? You have a highly non-trivial wave function, and this you have a highly non-trivial wave function. Okay. If these two wave function does not orthogonal, then they could have a small overlap. Perfectly okay. Okay. It's perfectly okay. Okay. It's a little similar to what you learned in your quantum mechanics. Two general states overlap, or sometimes they're overlap. Essentially the same thing. It's very generally happen. Two states can have overlap. They don't violate any causality, for example. That's right. Maybe if you're interested, you can think a little more deeply how to understand this better. Something related to entanglement. Okay, it's quantum entanglement related. Okay, essentially means a general space-time point in the field theory. After quantized, they are entangled with each other. Okay, they are entangled with each other. Okay. So, are there any questions about the computer? It's not a full computation. Okay, I suggest you can try yourself how to do the full computation. But at least now we understood how the two-point function looks like when the 2 points are time-like separated or space-like separated. And if you want to challenge yourself, of course, you can push you to higher point functions, right? I can try 3-point functions, 4-point functions, n-point functions, okay? But the point is, it's a little challenging because even 2-point functions, right? It's a highly natural integral, okay? And
你看这里是不是写反应该是先发 y 再发 x， 不然你那里插了个符号。
You mean x and y?
应该是发 y 发 x， 不然的话这样子到后面是一直上没有那个符。
Okay, let me check. No, it doesn't matter. X minus y is the same as yeah. If you switch x and y, you get the same result. Another question.
For the case of xy time-like, the same result finally diverges. If we do the
Which is
integral,
divergent?
after we integral over e, and this result will diverge at e to infinity.
You mean t?
E. The energy.
Ah. Oh, that's true. Yes. But it's understandable, right?
Yeah. So
because
we understand
this is the overlap. The overlap. This essentially means that when you want to consider the infinite large capital E, means you consider the overlap in this infinite large energy regime, which means the 2 points may be very close to each other. Okay, infinitely close with each other. This is so-called UV divergence. Okay, yeah, it's understandable.
Okay,
yeah, that's a very good observation. I think it essentially means that when you consider these 2 points are almost coincide, then you get a large overlap. Yeah. So as you can see, there's a lot of rich stuff you can try to compute or challenge yourself and compute as many points correlation function as you want. In principle, all the tools are ready now. Okay, you can do it. You can do it yourself. Okay. But now we want to switch something else. Switch to something else. So these are the endpoint and correlation functions. We want to look into more details of some more physical objects. For example, we can try another quantity. We can try to talk about this. We mentioned many times. When now all the field becomes the operators. Because of these are operators, we can talk about the commutator. We talk about commutator. So another quantity we can try to look at the commutator. Which is phi x, phi y. Now you skip all the facts. You will agree that all is their commutator. Now if I hand you such kind of commutator, you should immediately realize that this is the number. Can you see that? Why this should be a number? The output of this commutator should be a number. Okay. It's not an operator anymore. Because these are phi, right? Why? Because phi is some highly non-trivial linear combination of AA dagger, okay? And then if you commutator, either AA commutator is 0, A dagger commutator is 0. The only non-trivial thing is the AA dagger commutator is not 0. But even though it's not 0, it's a number, okay? It's not an operator, okay? Because this was determined by my quantization condition. My quantization condition fixed this A dagger commutation relation always to be a number, okay? It's not an operator anymore. So once you see such kind of object, you should immediately realize this is a number. So if this is a number, then it means this commutator will be equals to the expectation value. You see that? The trivial fact, right? The trivial fact, right? Because if it's a number, then you measure the expectation value, it's just equal to itself, okay? If it's a number, it's not an operator. Then what? Then, of course, you can just try to calculate it, right? You can try to calculate. So I can calculate this. Why? Because it's a little more complicated than this one, you see? Okay? This is the 2-point function. See, there is the commutator here. There's just the 2 terms. One term is the phi x, phi y, another minus phi y, phi x. You see? Okay? If you know how to compute this one, then you should be able to compute it. Okay? Then let's do it. Okay? Let's do it. Then as what we performed there, let's plug in the operator definition of this phi y. Care about there are 2 different terms. These different terms switch the x and the y with the minus sign in front. Then you realize that you get again 3-dimensional integral. Okay, the 3-dimensional integral. The first term will be of course same as this one. Okay. So you can guess the result, right? Here you can guess the result. The first term is minus p times y. What about the second term? There should be a second term, right? There should be a second term because we have 2 terms in this commutator. And the second term compared with the first term is just switch x and y, see? And with the minus sign, right? So the second term is e minus p y minus x. So I insist this x minus y, then the sign flipped. So here I have to get plus I dot x minus 1. Clear? Clear? Is that right? Now, as we saw there, it's not an easy integral. Here, the same thing happens. But now let's do some little trick, okay? Because we already learned a lot of mathematical tools for physical questions, okay? We learned in the second year of undergraduate, okay? So look at this integral, we can do a little fancy trick or things to improve this integral, okay? Improve this integral. So in order to do that, let's first write this integral one more step, okay? So what's the point? The point is I can just, before I calculate this integral explicitly or straightforwardly, I can just translate this integral to some other type, okay? Okay, because this integral looks very symmetric. Look, there are two terms, right? And there's some more deep extra factors here, okay? Extra factors here. Now I can write this integral in this form. Without the calculated, okay? Before I calculate, I write this. Okay. Right, it's trivial, right? It's trivial, right? Right. Trivial. I just shift this 1 over 2 omega p for each, okay? For each. And as we understood, this p0 is not independent. It's not independent, okay? P0 is essentially omega p, okay? And just rewrite this term and then shift it to there and just sort of minus sign here and then the same thing, okay? I did essentially nothing, but just rewrite, okay? Right. So what is this?
Yeah.
This should be very intuitive, no? How this looks like. I suppose you know you should be able to do a lot of different integrals, right? Different types after your course with this mathematical tool, physics. Very good. Then this integral 2p looks very like some result from some contour integral. No? Do you still remember? Your complex analysis, you deal with a lot of contour integral, right? Okay? Once you have contour integral, you should pick up the residue, no? Of the poles, okay? Now you can prepare, this is some result coming from some contour integral. Okay. 就是微道积分。OK， 我们在数学物理方法里面应该学到的是微道积分。微道积分。当我们在做一个微道积分的时候，我们是取留住。OK， 取留住。So these two terms looks very much like. Then you can prepare. This is some result out of some contour integral calculation. You can write down the original contour integral. Like instead of calculate this one, we actually go back. Okay, we view this as the result of some other calculation. We go to the origin of that integral. One more step. Okay. Then the question is, what is the contour integral? Give this kind of result. Can you guess it? Can you guess it? Certainly. Look, here I choose to write in this way. Then certainly the contour integral has to be associated with P0, no? Right? Because when you do a control integral for P0, you know, this term might look like some, you know, some residue calculation at some poles, right? Then where are the location of the poles? The poles will be precisely at this point and this point. Look, right? Okay. Of course, we also know P0 is a real variable, right? P0 is real. Why? It's energy, right? P0 is a real variable. Then, if you suppose you have two poles at these locations, then you can imagine that actually the integral you are doing is you're doing the P0 integral along the real axis, but there are two poles. Okay, that's the thing you looks like you have to you want to do in order to get that kind of result. Look, right? What I mean is, yeah, this has to be related to some P0 integral. Okay, some P0 integral with something inside some integrand can reproduce this result in this big bracket. Okay. Now the next thing is we want to try to write down this P0 integral. Which kind of integral can do this? And we get some. That's one thing. And we get some other messages that there should be two poles located in this way, which means that suppose this is my real axis system. Now there should be two poles. One is minus omega p. Another is plus omega p. Okay. And this is my real axis. Okay. Real axis for P0. Look. Okay. Right? Then, as we learned already, when you do such kind of real axis integral, but if you have poles, you have to do what? You cannot just pass through the poles. Okay. Okay. Not pass through the poles because the integral is ill-defined. Okay. What do you do? You do move around, right? You do move around. You move around to avoid the poles. That means we have to choose some contour. Okay? That's what we do. So in this case, for example, you can choose a contour in this way. Okay, this is one way, right? It's not the unique way, but this is one way. See? At least this contour makes my integral well defined. Okay, well defined. We still don't have the concrete formula of the integral. So what is the integral? So the remaining part has to be something like this. Look, right? So these are the common factors. And you pick the value at this position. So the integrand, right? That once the integrand has to include such kind of factors times p dot x minus 1. Okay. And which kind of factor can include these 2 points as poles? Right?
分母上面是欧米伽 p 减微和
That's right.
p 加。
That's right. Certainly, p squared minus m squared can do this. See? Why? Because p squared equals to p0 squared minus p along squared, now minus m squared. Okay? So this kind of denominator, okay, pick up the poles. Because P0 is my variable. Look, this means P0 has 2 poles, right? 2 poles is essentially the plus omega p and the minus omega p. Look. So it looks like it seems like this contour integral does the job. Okay, that's what we want. You can check yourself, okay? You can check yourself. Now I told you which kind of integral you can go back to check. Now you should be able to calculate this integral very quickly. Because this integral, this is the contour, okay? And these are the poles. You know, if I do the integral in this real axis, and I will choose the contour. Suppose this is the contour I choose, then you have to, you should be able to do this integral quickly. Then you realize that this is equal to this only when this equals to this one. This equals to this one only when x0 is bigger than y0. Okay, that's also the important condition. Why? Anyone care why this is the essential condition? Why this is the important condition? That's right. This condition essentially tells you how can you close the contour, okay? 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 Look, as you learned in your complex analysis, okay? Now remind yourself a little bit. Maybe there's a chapter called, like integral and residue, okay? How you calculate the integral using this residue. When x0 is greater than y0 here, means the zero component of this x minus y is positive, okay? See? So this is the positive. This means you can close the contour from below, okay? Is that right? You can close the contour from below. Right? 还记得吗？这个叫什么定义？大圆体 ，OK。Very good. Very good. 为什么？How to distinguish these two signs or from which one below or above close the contour? The easiest way to justify this is just the from below means the P0 value. The P0 value can take I minus infinity, right? Right? Minus infinity. So plug into here. If your P0 is I minus infinity, then I times this minus I is positive 1. The minus infinity times this positive x0 minus 1, 0 is minus, okay? It's active. Essentially what we want, okay? We want, when the contour moves very far away, we want there's some decay factors, okay? Right? If decay factors makes the function looks very nice, okay? You shouldn't diverge, but you should decay, okay? Better to decay. When you decay, then the integral over this piece of contour will become trivial, okay? Which means you can add up this piece of integral. It doesn't matter, does not change your result. This means we essentially can close this contour, okay? Then compute this closed contour result. Use that result to achieve this original contour, okay? Is that clear? That's what you learn in your complex analysis, okay? Do you have any question? This
气是这个重量的，可是闪光或下不来不怎么细啊，是那个更小件，那就是我们把小同学来是
This is important. So let me write the. This relation more explicitly means that when this condition is satisfied, one can close the contour. From below. And from below means what? From below means we can pick up two residues. Look, right? Right? If suppose you close the contour from above, you get nothing. No, because there's no poles in your inside your contour. You get nothing, right? It's zero. The integral is zero. Means inside region the function is analytic. Okay. If the function is analytic with the contour integral, you get nothing. Look. Only from below you can pick up two terms, right? We indeed need two terms, right? Because we want to cook up some contour integral to reproduce these results. Okay. That's why we need close this contour from below. And reproduce. Reproduce what? Reproduce this bracket result. Suppose this is equation star. Then, as I said, if suppose the x0 is less than y0, we cannot achieve that purpose, right? Cannot achieve that purpose. But you can still ask what do you get? As said, we get 0. Because in this case, the complex analysis tell me, in this case, we can only close the contour from above, okay? The sign flipped. And the contour integral in this case is 0. Okay. To be 0. Is that clear? This means what? Now let me summarize a little bit. This means my initial goal to translate this complicated object, two-term things, into a contour integral. We can succeed, okay? But under a condition. The condition is this one. Under this condition, this is really equals to this one, okay? That's the relation. Is that clear? Now, let me write this relation. This is the important relation. Let me write this equation more clearly. So, suppose we define. Now I can change my mind a little bit. Forget about this initial purpose to just translate this complicated thing to a contour. Instead, now I want to view, because this contour integral, if you fix this contour in this way, okay, this way, then the integral is very defined. The integral itself is very defined. Okay, is that okay? This integral with the specification of this kind of contour is very defined, perfectly very defined, right? Is that clear? What do I mean by very defined? Because it depends your parameter. Now this contour, inside this contour, usually x minus y are parameters. They're not variables, okay? Then depends on your parameter, meaning depends on x0 and y0, which one is bigger, okay? You can choose either close the contour from below or above, okay? Depends, okay? But even these two situations are different. It doesn't matter. you can temporarily you can forget about this close the additional piece of this closing. Okay? Forget it. The point is this integral with only this specification of such kind of control is a perfectly well-defined integral. Okay, it's a well-defined integral. We realize that, then we can try to define what? Define this integral with the contour as some new object. Okay, define the integral with some specified contour. Let me just sketch the contour in this way. We can define the integral with this contour. Put it as a new name, as dr minus y. And this is defined as using some theta function, y theta function. We can justify it immediately. Let me first write it and then explain. Okay. I can do this way. I think this integral with the specified contour is more important or is more fundamental because as explained, it's very defined, perfectly very defined. Okay. Now, let me look at the right-hand side to interpret a little bit what is the meaning of the right-hand side. Right-hand side, there is a step function. Do you know what is a step function? Theta function. This function is a step function. Okay. Only the variable is positive, it is 1. Okay. If the variable is non-positive, it's 0. Okay. It's negative, then it's 0. Which means that this theta function controls this right-hand side only when x is 0 greater than y0. Okay. It equals to this commutator. You see? What is this commutator? This commutator is this one. Commutator is this one. Okay. Now, if x0 is less than y0, because this is 0, okay? So you get 0. Look, which means this definition, this kind of definition, really precisely agree with this integral, of course, together with these three, together of this three dimensions. This kind of integral with a specified contour indeed agree with this right-hand side definition. You see it? Is that clear? Okay, good. Now, this is nothing but one more piece of integral for P0. We can put them together. Okay, we can put them together. Okay. Don't forget one more thing, because when you perform this integral, when you pick out the residues, you have to divide it by 2 pi I. Remember that? Right? Then we have we have 3 2 pi. Now we have one more 2 pi. Okay? We have four 2 pi. Then put everything together. This d r x minus y has a very simple form. It's just a 4-dimensional p integral. 2 pi to the 4th I e squared minus m squared e minus I p so x minus 1 with what? With that kind of contour. Okay, that's it. Okay. I essentially replace this amount by a single one more P0 integral and combine with this three-dimensional integral form a four-dimensional integral. And I get that such a simple form. Okay. Okay. Is that okay? Such a simple form. The magic thing here, or the subtle thing you have to pay attention is, in this integral, P0 is a variable, okay? In that three-dimensional integral, P0 is not a variable, because P0 is not independent of P vector, okay? Okay? But it's okay. I blow up one more integral for P0. I can view P0 as a variable. Because I proved that these two are equal. So now I can simply view that all the components of P are variables. Okay? It's a four-dimensional integral. Four-dimensional integral. And in particular, I specify the contour. Because if I don't do this, this integral is year-defined. Why year-defined? Because they are poles. Okay? They are poles in the real axis. You cannot pass through the poles. You have to specify the contour. Okay? Then I specify the contour in this way. How to move around these two poles. There are two poles. Okay? If I specify this, then this integral is perfectly well defined. I can take use of this mathematical fact to define some new correlators. Okay? Called dr. Okay? Give a new name. dr. Certainly, dr is not completely equal to this commutator or two-point functions. Right? It's a slightly more non-trivial. Look, because there's a theta function. Okay, that's what dr. That's what dr is. Okay, this theta function tells you that only when there is this is positive, then it's non-trivial. This is negative, then dr is equal to 0. Because of these physical properties for dr, we call dr is a retarded Green's function, okay, or retarded correlator. Okay. How to translate retarded? That's right. Very intuitive, right? Feature. Because this is that function. It's only non-trivial when x is later than y. Okay. Now what do you mean by retarded Green's function? Now, since we touched this is a very beautiful story. Look, I mean, if you write this in terms of this form, then it's not something more difficult, but something much simple. Okay, why do I say this? Look, what is this? Think about this part. What is this? What is this? What is this? Hmm? No, my question is how to think about this object in the box. This is a Fourier transformation. Okay. This box is the Fourier transformation of this guy. Look, right? Of the X space correlator, right? It's just a Fourier transformation. Look, no more than that. Right? Now, using this contour trick, I successfully translate the correlators in the momentum space. Okay, using the Fourier transformation, because it's just a Fourier transformation or Fourier decomposition. Okay. But here we want to be very careful about this contour. As we emphasize, this choosing of the contour is extremely important. Otherwise, you could get different result if you switch to different contour. Yeah, that's what we want to do next. We want to choose different contour. Now, since contour is clearly the choice of contour is important. What if other contours? I don't want to choose this one, okay? I don't want to choose this one. For example, I can choose this one. I can first from below, getting a void, and then from above, okay? What about this? What about this? Okay. This is my choice, right? You should allow me to do whatever I like. No, the point is I don't want to change this object. I just want to change the contour. Okay. So if you don't want to change this one, always two poles. The point is how you get it surround your pole. You have different choice. Then this is my single. This is my one choice. Okay. This is the A choice. We already understood that with this choice we get physically retarded grid function, retarded correlation. Okay. Now since I get this feeling. Okay, there's a freedom to choose contour. That's what you told me. Okay. Now I'm allowed to do other choice. For example, I switch to another choice. These are the two poles. Now I choose to surround these poles in this way. Okay, and I have another definition, right? Now I write this as df. Look, here I use R, but now I switch to another S. Okay, df. So I define this 4-dimensional integral with this particular contour choice as my new grid function or correlators. Okay. Now, you might say, okay, it's so complicated. Every time you define a new correlator, you have to draw which kind of control. It's so complicated, right? It's so complicated. Then there's a trick to avoid this one. There's a trick to avoid this. You can forget it by using some other trick. This trick, I'm going to now explain which kind of trick. This is called I epsilon trick. Okay. Now I can add a small plus I epsilon following this p squared minus m squared to achieve the specification of such kind of contour. Okay. Can you see why? Because epsilon is a positive small number. Okay. Constant, which will descend to zero eventually. So why? Let me explain. You can actually easily check yourself. Because of this one, because this is I epsilon shift, my pose was also shifted a little bit. Look, right? With this positive epsilon plus I epsilon, I should work out my new pole. So what is the pole equation? The pole equation is p squared minus m squared plus I epsilon equals 0. This is my new location of the poles. Okay. So work it out. This means that your location of your poles, which the p0 equals to plus minus omega p minus I epsilon. Okay. Now epsilon is positive, and this is plus minus. Where are these new locations of the poles? Okay. This essentially means for the positive omega p, where is my positive omega here, right? For the positive omega p, I get minus I epsilon. Means what? Means it's lower a little bit. Okay. The original pole was shifted downstairs a little bit. Okay, with this I epsilon modification, right? And oppositely, the other one, the minus omega p pole, this minus plus this minus was plus, okay? Plus I epsilon. Epsilon is positive. Was shifted above a little bit, okay? So this I epsilon shift or I epsilon modification essentially adjust the location of my two poles a little bit, okay? That adjustment essentially achieves the goal. I don't need to shift my integral control for P0 because the pole are shifted. I don't need to, I can go through the real axis without any trouble, okay? Then I don't touch any poles because my pole is shifted a little bit. But that shifting is essentially the same as the specified control in this way, look, right? In that case, the positive will shift downstairs a little bit, relatively the same as you choose your control in this way without shifting your original pole. Same thing. Contour integral tells us the details of that shifting doesn't matter, okay? Okay? The real matter thing is specify your contour. Where are your poles? Eventually pick up the residues, okay? And the point is, after this I epsilon shift, I always send the epsilon go to 0 in the end, okay? So the only role of this I epsilon modification is to specify the contour. Okay. Is that clear? Eventually, I just set epsilon to 0. Then epsilon is gone. You see, in the intermediate, I use this I epsilon to specify the contour. Okay, that's it. So with this modification or shift by epsilon, I can simply erase this one. Okay, I don't need to specify anymore. I just keep in mind, everybody agree this I epsilon means in this way. That's it. Okay, everybody, there's a common agreement. The agreement that whenever you see an I epsilon, you should treat the epsilon is a small positive constant. Eventually means after all the calculations, I send epsilon go to 0. Okay, this means that the only role of this I epsilon is to help me to specify the contour. That's it. And in particular, in this way, it specifies the contour in this case. Okay. Then it's very cheap, right? I don't need to do this drawing every time. I just have to write in this way. That's it. Now, then how to compute this one? Well, I explained how to define this one, but how to compute this? And again, we have to discuss different case, right? Because in order to compute it, you have to specify more. So when this one can, as before, what we did essentially what we did before, we can close the contour from below. When you close the contour from below, what do you get for the DF? In this case, when you close the contour from below, you pick up which residue? You pick up only this one, okay? You close your contour from below. You pick up only one. This is a void, okay? This is not inside my contour, okay? Because I close my contour from below. I only get this point contribution, which means when this condition, under this condition, when this is satisfied, this DF, you only pick up one contribution. And I choose to perform or finish the P0 integral first. Then what I get is this. What I get is this one. So what is this? What is this? This is the integral we worked out in the very beginning. Okay. Okay. What is this? This is the dx minus 1. It's a 2-point function. Okay. Don't confuse yourself. This is the 2-point function. This is the df. Okay. df is slightly complicated, but only when under this condition, you pick up only one contribution, then you get the dx minus 1. This is a 2-point function, and this is the so-called Feynman propagator. Okay. That means Feynman. Okay. Why we using this labeling? Because it's a very physical propagator, as we will see. And when x0 is less than y0, one can close the contour. From above. From the above, okay? From the above. If you close the contour from above, then you only pick up this one. Okay? Only pick up this one. This means that df x minus y under the condition x0 is less than y0, you will get this plus IP for x minus y. And what is this? There's a plus, so this is d y minus x. dy minus x. So put everything together. Put everything together. EF can be written as sig function with a 2-point function plus another sig function with a 2-point function. Leave x and y. Okay. Just do nothing but just organize these two results together, right? From the contour integral point of view, you have separately discussed these two cases. Well, once I know these two cases result is nothing but the dx minus y and the dy minus x, then I can put them together using two sig functions. Clear? Now we have one more important step. Now think about for a few seconds. What's the meaning of this structure? This structure. What's the meaning of this structure? This structure means this correlator somehow always prefer which operator is later than the other operator. That operator should be located in the left. Look, right? This x0 greater than y0 means time is later, okay? Phi x is located in the later time coordinate, okay? Then I have, in this case, I have phi x and phi y, look, okay? Now, suppose if y0 is later than x0, okay? Then the phi y has to be located in the left of the phi x, okay? Right? That's the structure. For this reason, we can write this using something called the time ordering operator or time ordering operation. Okay, time ordering operation means who is in the time coordinate later, who has to be located in the left. That's it. Right? It's very intuitive, right? Because let's suppose I always evolve in time direction from right to left. Okay, I start from some state. My state now meet some operators. Okay, I think my state evolution in time direction from right to left. Okay, this is my initial state. This is my initial state. Now I meet some operators and then other operators and then overlap with the vacuum again. Okay, that's my understanding this correlation function in physical way. Okay. Is that clear? If you understand it this way, then it's very easy to understand this time ordering operator. Okay, the time ordering operator always means which operator has earlier time, it has to be in the right. Which operator has the later time, it has to be on the left. Okay. Then you perfectly agree with this definition, right? Right? This definition is just using the step function to do the same thing. Okay. You can check it, right? Suppose the x is my later time operator. Then I only have this one. This is 0. Okay. Then I only have this one. Suppose my x is my later time. Suppose my y is my later time. Then I only have this one. That's 0. Okay. This means I suppose I'm a god. Okay. I can observe which operator is has the later time. I just by force let it on the left if it has later time. That's the definition of time ordering. This is very, very important concept. OK， 我们休息15分钟。
快口会正确倒计，快口会正确倒计，快口会正确倒计，快口会正确倒计。
一样的，这个不是唐国子，
也有物理的问题，因为一直是没有意思，就不能这个一般人现在提高时间开始我觉得挺麻烦。那就是整个好几次稍微在这个边，专的意思就是你要取一辆状态到另外一辆状态，符号体系还是高一点的节奏。看一下，我看他也没有讲，没有讲这个。我之前研究过这个轨道的问题，是我觉得它给出的话是不准确的，就是比如这个是从这个是到这个是应该差一个多少，因为算这个轨道再一个是地方嘛，那我们只考虑就是都考虑 scale 这部分也是有指的，这部分也是还有一定的指的。这个题我原来是有定义问题，我是否把这一块定义进去？
对，我觉得这个好像但是就是这个吧，就这个好像就这个积分的话，好像不等于二排的
太排，因为这一
好像要算，好像还要算
AP 是的这个 AP，
但是我有点忘了，这个学太久。
所以反满那个方法真的非常精妙，把这些问题全部解决了。 就是如果我们要算这个其实这一步的对，它应该是派函。
对，就如果是整个积分的话，就如果你的起点在这里的话，就不能简单的用那个。
你右边是0的话，对，
应该还有一部分，这部分应该还有一
左边是0。
啊，
这一部分积分是
有没有一个1/2的区别？
对，然后这一部分是又1，这里是2派，然后这里会有负派，所以加起来应该是派的，算不了。这又刚好有2的时间开始，但这好像在结果这没有。因为你如果要把这一段定义到你的这个积分里，
这种好像就和你的起点完全在中间。
所以白板那种说法最好的，我觉得最好的办法就直接一条这个一个基点来这一个基点，完全不用考虑，就只有一个基点，只有一个这个基点，然后这个，这我觉得是白板最厉害的。
那你就加 i 这种，就相当于是你可以把
这组上平一点，对吧？
这个
那个是 exactly 然后这个结果，然后这个的话就让你看，
就是确实可以。只是觉得第二条那个是所以乘以2倍还是
就是这一步把进去。
第二条不是
不是也
翻门法不对。
首先，这个可能是来自 SK 书上的一个写的不太好的一个问题，就是他说，就这个积分，它是不是就等于在这个维度上完成问题？但实际上，用这个维度积分之后算出来结果就反而是就是 retarded rate， 就是它前面得乘一个就是 delta 是负分子，而不对积分。
对，就是 retarded。
对，所以说就这个东西这一步它应该不能说是等于。就如果要分个指号的话，那要还原就必须得认为它是一个纯值积分，然后积分加上这些维道，然后加上大引符之后就等于0，就才能把它。对，就是
这个不是严格相等，就 conditional 相等，只有在这个条件下，在这个条件下等于这个积分是这个维道。这个积分为这个维道不 always 等于有条件的出来。
是不是？如果我们这个事上真的想算原来这个式子的话，就是如果不看这个，那么就是如果就是它也可以还原出一3号，还原出一个维道积分出来，而这样或者说就变成这样一个组织积分，这个组织积分的计算应该是就不依赖于到底上面一道还是下面一道，就类似你刚刚说的这个问题，就是你从上面一道会出一个比如说会变一个负的 i 派，但是又包了这个东西出来，而从下面一道就直接变成一个正 i 派，不过就这样子一算
我这边买主值积分，主值积分在这儿有破我的已经有点坏了，必须怎么传给到？
对，就是组织积分要算它，必须得用维道去把它去给反推出来。
所以要 specify 维道，就是现在用维道来定义 correlate，
对，
这样比较 systematic。
所以逻辑上来说，就后面定义的那种，就是各种，比如说各种费曼传播子，就它其实已经，就它算的人是这个维道积分，但它并不是说我们，依然要算这个式子。
right， that's of course， 这只是一个 building block， 我们要讨论更多不同的。
OK，
你现在缺点是要用维道去 classify 不同的考虑，有不同的维道的定义和它的
这样。分法这个样子，没有关系。
这个没说清楚，不是没关系你现在问题是什么？就是我觉得这个顺序是对的。写的顺序是对的。把这个积分算出来。
我发现这个问题，这个想法这是后面， 是我谈。
心态上
就是比较啊，是这样的。对，看个经验，就是这个一个地方，有 AK， 这些都是新单位的，对，应该是 AK， 这个就
那这个至少不讲，
不是还没人来，
但是那是比较
一般鹏飞也在，一般鹏飞也在打，就是现场拉着开始
就是他
用是不是有个 AK？ 它这个是 X 那我是 AK
但是不是用的，不是用加减减减吗？用加减减减的不是应该是 IPS， 因为这样子才能湮灭是一个 IET 啊。
它在这个点就相当于往下了，是 P，但是它其实在演示，它会
是的，我首先是个 K 啊。第二个是个 K，
你们写的
是我写错，哦不对，右边
前面是 K，
右边应该是应该这个是2跟
对，
然后 A 加个 P，
对，
然后那个是
然后 AK 跟 A 加对应的那个这样做出来这个，
它和它那个是对应之后是个单词。
对，是个两忘了。
哦，没有讲，
它特别微信的一方减 M 和加 H， 然后是它的矩阵是然后太平好修。
我用这款那个
一般这个对子，这两个对子是
就认为
对吧？一个这个等于对，
这个方案
对子还是 AK，
这个方案应该是 back 的
AK 加 AK，把两边都长去，
它的分数是这样，
就两边长，
还是个考来
这个差零是 A， 就是这个差零。
就如果你用这个的话，这个就能打对。
哦，我知道这个就在记得
刚刚那个的话，就不需要这个方直接
对，come from here，这不是很清楚的吗？就是复合。
P 方减 M 方分之一。
那可能也是考完就是你就那样说这也对，
是这个是我要不可以，它这有个
而且它这个不想就是按例子决定了对应想要一个负 IET 的话，应该是 A 单个和是负 IPI，
就是够是另外里面就是一点这种推迟式，就是就从一个原点发，
因为就是
一段时间以后到那边，
因为
推迟的一个响应。
这样子我把它作用到一个基态上面激发出一个例子，那它那个这个项里就是单粒子的薛定谔是一样的，是E 的 I， E 的负 IT，
时间以后是
它
负 IE。
你看 Haskell 上面有一条这边话你都知道，大家没用的，是一开始是一个自由传播的一个波色子，然后它会有一个 source 进来，有一个 source， 我这个 source 的影响之后会在一段时间以后，它的一个影响是用 retarded 的这个 refactoring。
和这个
没有 sharp 的
后面的 recording， 然后这个它是我的这个
但是重要的是你要 make everything
它这个范式它为什么是有
算的都是重，
它里面还有重量吗？
那么多才选这种这样，这边你也可以弄一个重量。
它这里应该叫做大于 y， 粒子上面就是粒子态上面。这边看小于 y， 就是那个粒子态又一个粒子下来，是一个怎么复写？对。不过它这个经过不算大，没有看那个一点的话，但这里但不是小于小线。小于或者动作好像对，我说有把方向回去了，但是我一直没只有找那个找上去。1号为
但我们这个分给是0.0，很多东西啊。
为什么来？有，之后今年上海有它整一区，这个伟大的更伟大的神经
这摆出
这个是这样小的地方，要不要来见到谁？
我特别想拍一个电脑对我这种跳，因为我之前翻那个是一个主色，就是
它是
3个
全可以打我。
格色是
对，这里哦，刚刚有个
前
这里
前
具体讲用，这是在还要送真大并没就很清楚。
他用这个
实际上我们可以更
去掉
这个方法，这个点相对应的，
这是一个
咱们不看回答，因为
他现在这个皮就不会
对对这个只是为了
也算是要条件。你其实你第4批积分是没有，
你是怎么获得
对它对应的不太
对，就这种分数比较好，对对
那些虚例子，不是这个是一个区别，就是啊，原来就是区别，
这个
啊后面那个你坏了，实际上就是用一个之前就这个是推迟10周，这个是可以把清干净了。是用这个其实物理这里指法这里要被加这个变值拉值这个项一个小的这个技巧。这个通的节任务起来的话，它还是要少的。
可以啊，可以啊，可以。
就你的积分就是说，
对，跟创我觉得应该可以吧？那写一下。
然后是就这种那个，如果你这个定价的话，还有一条是，然后
对对，一定是死死让
只要让命令那个祭典在哦，对，他下定义
天晚上，
然后下多少多，他也定义基本上绕过2步，就少了。这个他针对顾客，你这个正常的这种就一条推荐，没有然后就比如说那种感觉，其实就往上面发，那也不对吧？眼睛往上面，对，他能连积极的或者你感觉因为这个不能啊，就是啊，包对，他这种这个哦，直接从积点传入，那没有定义的，这个定义是
定义，
那不是方案的吗？
没有说这些东西是我额外加上去的。
因为比如说，正常就可以这么正位方，它有点在这个下边的话，这个基本上完全然后这些时候，它也可以在第一过程它也是包括这个扛错的，关键的话它往上面绕，你往下面绕的话，那个直接不一样。那你这有什么？
就那个
OK， 这是换的是说，直接这样现场定义的积分是1.8，作为一个不分不写是大批到然后我并不是说我要让这个 integer 所以就是我再加多几分这个意思啊，就你要做选择，因为你就一定要是你肯定是正常的。这样会呢，就用那里面重新去一计算的。
就是说你弯，因为说是你相当于那个经典上我的那个完成定义的方式是这样，这个问题是说发散的你说为什么写个 P 或者
这个
那这些就是点名方式，这个东西是完全不一样的，就是它思维的好，这个没然后自己发展的不要的，我觉得怎么了？要在下边转，是我那个是
PK 那张给我展开。是我写错，
科学主持的问题。
哦，对不起，我真的讲这个话。好像是因为这个，就这个 PK 它应该等于这个。对，一上才对。
就是一个是分体的习惯，会需要只有一些
对，
一不是有30小时，
属于不可能。就是本来是一个来反思的东西，只有性。这非常的多，相对品质感觉就是有点是一副厂，但是这种还有这个多，就是
大部分
就是我一般的话变成个连续的东西，没有气嘛，你觉得？对，因为你
让我们坚肯定是早更有个对称性的小动脑场类。
一般让我好像记一个那个无穷号都会。
这个是
分别只有无穷对线陷入无穷加无穷关系。
没有说这个因为会商店，大一点的话就一变地啊，
对吧？
得到的地
这个比例
微信这个
地方点的方式比较好，
也可以等于替换成
相互然后这个时候对吧？
Okay, let's continue. So during the break, some questions from this small arc contribution. Let me make the point more clear.
所以是
In order to make this original integral, which has two poles defined, we don't add some small piece contribution. We just change my definition. Okay? I change my definition, meaning that I define the new integral along this contour as my definition of my new correlate. I just throw away the original year-defined integral. In that sense, whenever I specify my new contour, I have my new correlation function. So I don't need to include this extra piece because I don't want to view that this is an extra piece. This is my whole definition of this correlate. So we end up with some time ordering operation here. This time ordering is really some ordering by force. Okay, it's the ordering by force. So we have this contour there, this contour. So what else? So you can imagine you have two more choices, no? Right? Because I have two, up and lower, and I have two by two, which is 4. I have two more different choices. See? So what are the two more different choices? You just plot it. See? Because I can go from the both poles. I can go from below. Okay. And I can even do something weird. We can opposite to this one. I can, for the first, I can go from above, and the second, I can go from below. Okay? And totally, there are 4 different choices of this contour. So 4 choices of this different contour specify or defines 4 different correlators of gradient function. So I'm not going to the details because I don't have time. So just plot these 2 more. So for this one, we define this way. Define it this way. Okay. So this is A, dA. A means what? Is advanced. This is the retarded picture, advanced, 超前. Okay. This is the advanced correlate of gradient function. essentially defined using this control. Using this control. And there's one more, right? If you want, let's use df tutor. This is opposite, completely opposite to df. Okay. So what do I mean by that? Is again this integral, but now the opposite to that choice. Okay. I can first go from above and then from low. So this is the df tutor. Okay. If you are interested, go to understand what is the physics about this df tutor. Okay. So these are totally four choices. Now I mentioned already all these four different correlators are Green's functions. Okay, you already learned the definition of Green's functions in your mathematics group for physics. But you should check it. Why these are the good Green's functions? Green's functions have to satisfy some an equation, right? An equation equals to some delta, right? Some differential equation, second order differential equation equals to delta. Only those functions, solutions for those functions are called the Green's functions. Remember that? Because the Green's functions are propagators for the delta source. Okay? That's the Green's function. Now you should check. You should check whether these are Green's functions. For example, you can calculate, you can check box plus m squared. If I act on the dr or df or dA or df tutor, it doesn't matter. You can check for either. You check this. Whether this gives you a delta. If it gives you a delta, then it's really a Green's function.
我问个问题，因为 advanced 的它是不是要多加个负号？
Which one?
那个 dA， 就是它的积分路径变成了逆时针。The advanced function。
Okay.
也就是会多出来一个正负号，相比之前。
Where in front of for which? You mean the final result?
就是 advanced 的那个维道，它相比那个 retard 的那个维道，它是叫什么逆时针的变成，也就是说它相对来说多出来一个负号，比上那个非时针来说。
No. At this moment, all the errors you see not the same direction, not this one, but this one, right?
Yes.
This is to the right.
Yes, but
This is also to the right.
yes,
Whether it's the clock or anti-clock, it depends on how you close the control. If
Yeah.
you can choose both.
if you close the
Yes.
above,
Yes.
And it multiply 2 pi r.
Yeah. Fine. Yes.
It would
Yes.
produce r.
Definitely yes. Yes. This is the definition. If you get minus, then you get minus.
还是靠 minus 这个。
This is the definition. This is the definition. Okay. Good. Any other question about okay, before we go to the Green function track, how about all these four different kinds of correlators? These are very important for different kinds of propagators. They are physically very different. So we have retarded, the ones that we have Feynman propagator, we have even the weird one, df tutor. Okay. They are specified by the contours. Now you can check whether this is a Green function or not. So how can you check this one? So let's do it. So what is this? Just act on. This is the box, the operator, right? This is the partial. The partial mu. Then act on this one. We already know what is the dr. Right? Then act on this one. Then what you get is partial square theta, because the dr is defined by theta with the commutator. Right? Because dr is the theta with the commutator. Now you have a box operator. Then you have three terms, right? First, act on the theta, and their cross term, which is the twice partial mu theta. Partial mu, the commutator. And the last term will be the box act on the commutator. Okay. That's it. Those three terms, right? Let's do it one by one. Now let's observe how to calculate these three terms. Now the first question you might ask, once you act one's derivative on this theta function, as we all know, what is the result? The delta, right? Right? Derivative of theta function is their function, right? Is that clear? But this is twice derivative, okay? What happened for the twice derivative? How to calculate it? That's the first question. Now for the second term, similar because this is the delta function, okay? This is only a delta function. Now there is a partial mu here. Don't forget that this partial mu actually means the partial with this dx mu, okay? Dx, the acting on x, okay, not y. And that's first. Another thing is, as you can see, because this theta function is only cares about the time direction, right? It's zero component. You see, zero component, which means that only when mu equals to 0, this is non-trivial. Okay, you can forget about it, or mu is not 0. Okay? So when mu is 0, this partial mu essentially means the partial time direction. Okay, time variable, and the action on x. Essentially, the second term gives the phi x dot, okay, right? So what is the phi x dot? X dot by definition is pi. It's pi. Remember that? Pi is the conjugate of phi, okay? So in that sense, I can compute the second term because this is delta multiplied by some pi commutator with phi. And pi commutator with phi by quantization condition, we know what it is. Okay, it's a number, okay? Is that clear? Now, last term. Last term, this box is purely acting on this one. Okay. As said, this is acting on x point. Now, this box plus m squared acting on phi x. What is that? It's equation motion, right? Right? By equation motion, this is 0. Okay. So last term disappeared. This term is some delta and some commutator of pi and phi. What about the first one? The first one, to deal with this delta function derivative of the delta functions, we will do the integration by part. Okay. What do I mean by that? Because some delta function times something, we should always understand that kind of object together with the integral. Okay. As you learned in your second year undergraduate course. Okay. Okay. Because delta function is essentially defined through the integral. Okay. So you have to think about how to do the integral of this given object, carry delta functions. If you think in that way, then you can safely do integration by part. Because we always ignore the boundary terms. If you do integration by part, then this is the same as the structure is the same as the second one, right? Right? Because now I have a derivative delta in this one. I do integration by part. It's equivalent to a minus sign delta times this one has a derivative, right? And that essentially becomes the second. So with those all knowledges and the careful calculation, you can indeed came up with a beautiful result. And this is equal to minus I delta for the dimension of the function. Okay. Then we we justify that this is indeed a Green function. Because I act by box of m squared, I get a delta. Okay. So this is a Green function. It's a standard definition. Theta is the standard definition of Green function. We learned it before. And you can check all others. I suggest you check all others. You can check this is for df. You can check this is for dA. Maybe even for df tutor. Okay. All these four are good Green function. These are Green function. Then let me ask you, what about the 2-point function? Is 2-point function a Green function? Is it true? We introduced the 2-point function in the very beginning, right? Just phi x by y. Is this the Green function? Hmm? Yes. It's not. Okay? It's not. We cannot act by box get delta. All these four are Green functions. Okay? So these four are the physical propagators, not the 2-point function.
我们就直接对它北道积分那个定义去操作 box 加 m 方，这样子不是可以很快的推出来它是个负 I delta 4吗？
Yes, maybe yes. Yeah, yeah, you can check it in different ways. Do you have any question about these four different types of propagators? Okay, so the next thing we want to discuss is about causality, which we mentioned in the classical field theory. Somebody asked how to understand that this is in quantum fields. Now we quantize the fields. We should come back to this causality. Okay, how can we see causality in these quantized fields? For this purpose, we come back to these commutators. Okay? We already know how to compute it. Okay? We know the result, how to compute it. So for the correlators, I think we wrote somewhere. For the correlators, we already understand that this can be expressed as dx minus y minus dy minus x. Okay? It's a trivial factor, right? Because combination is just 2 pieces equals to this one. Now, let's try to discuss a more physical consequence or physical indication to compute these correlators. What do we mean? If these 2 points are space-like or time-like. For example, if we want to put these 2 points are time-like or space-like, okay? If x and y are space-like, what is the commutator?
0.
Why?
Because to set thing.
Why?
一个是 I IP 点乘三维部分，然后一个是1的负 IP 点的三维部分，然后呢把它们 P 和 IP 它们之间对称了，所以直接 cancel 掉了。
对，它是对一个 P 函数来进行积分，是的，所以，就它这个积分肯定是O函数。
Okay, any other answer? It's very simple. We can conclude, right? We can use Lorentz transformation. Okay. Okay. What do I mean by that? Look, if x and y are space-like, one can Lorentz transform. Okay. One can do Lorentz transformation to transform essentially flip x and y. Transform x minus 1 to y minus x. Okay. You see? Because these are points are space-like. Space-like. Okay. Is that clear? I can do Lorentz transformation to realize this x minus y2 minus x plus y minus x. Because these 2 points are space-like. They're connected. Okay. This immediately conclude because here I just use Lorentz invariance. As you said, as we discussed at the very beginning, these both 2D are Lorentz invariant. Okay. If you can do Lorentz transformation to send x y to minus x minus y, which is essentially means this equals to d y minus x if 2 points are space-like. Okay. Okay. But if these are time-like, you have to be careful. Okay. Because time-like, they are not related by Lorentz transformation. Okay. You have to be careful. This trick is only for space-like. In this case, 5x, 5y, you conclude that this just equals to 0. Now, what happens if x, y are time-like? If these are time-like, there's no continuous Lorentz transformation. Can send x minus y to minus x minus y, or can switch it to x and y. Because of this, then the commutator is not there. This means what? This means this commutator operation really does the job to distinguish whether these 2 points are causally related or not. Okay? You see? This means in quantum field theory, if these are 2 points are causally related, then they will have a non-trivial commutator. But if they are not causally related, okay, then the commutator has to be 0. Because from the calculation, you can see it. This means the commutator is the proper quantity to justify causality. So inversely, I can use the commutator. A priori, maybe you don't know whether these 2 are causal related or not. Then the point is you can calculate the commutator. Okay. If I find that the commutator is 0, then I can say, okay, maybe these 2 points are causally unrelated. If I find the commutator is non-zero, then the causally related. The causality is related to commutator. The commutator of 2 operations. Not 2-point function, right? You can see. Now, 2-point function is just some overlap of some wave function or state. But a commutator really detect whether these 2 points are causally related. That's the next.
是这个是对天上去的，连续的，连续。
Even the 2 points are causally unrelated, means space-like, for example. Okay, causally related means what? You know, as you learn in your special relativity, you have a cone, right? In order to make the causal structure clear, you have to put a cone, right? You have a cone. You have a cone, and you can divide your space-time into the space-like region or time-like related region. And the point is, if the 2 points, even the 2 points are space-like, meaning the causally unrelated. Okay, they can have a non-trivial 2-point function, but the commutator must be 0. If the 2 points are time-like, meaning they are causally related, the commutator is non-zero. So commutator is a better or proper quantity one can measure to see the causality. Okay, that's the next here. So we have 20 minutes left. So do you have any question about this relation between causality and commutator? So let's now talk about some higher points, how to deal with the higher points, which is essentially very important when we compute Feynman diagram next time. So this is something called Wick's theorem. This is about we learned how to compute the 2 points. Okay, after here we learn how to compute the 2 points. Now I can ask myself, this is a free field, it's so simple. I can ask myself, why don't you push this calculation to higher points? Or in another word, how to compute something like this? T. Here I use T because T is some ordering operation by force. So it's better to using a bracket. The bracket means this time ordering cover which kind of up to where, okay? So sometimes I use a bracket, it's just a label. So the question is, if I have higher points, what are the free fields? The 5x1, 5x2, dot, 5xn. I have n points, and all of them are time ordered. Okay? How to compute this one? That's the question. Of course, one way to do it is by brute force, right? Because you know how to compute 2 points. You know, if I have higher points, just plug in the definition. Repeatedly use some AA dagger relation and the time ordering. Just plug in, and you might get some result. That's true. But there's a more convenient. Actually, the result is so simple. So, the result is so simple. So, the way to derive the result, I will summarize it as some theorem. Okay? Because in the beginning, it looks as this problem is very challenging. But it turns out the result is so simple. So people named this, summarize this process as a theorem. Okay. So-called Wick's theorem. The Wick's theorem is to how to deal with this calculation. I'm not going to derive this Wick's theorem. Just how to use the result. But you should try to prove it yourself. So what is that? So Wick's theorem says that result. Let me just try to show the result. To try to show the result, let me try to illustrate as an example. For example, 4 points. 4 point time order correlator. Which means if I want to compute, there is 4 points, and let me use the phi 1, phi 2. 1, 2 essentially means the location. If I want to compute that the object looks like this one, the result is very, very simple. It's just you contract these 4 points in different ways, put them together, add up and then add up. Right. This is very intuitive. Look, as a result, I have 4 points. The result says that just put 1, 2 together, 3, 4 together. This is like a pairing. Okay, I have 4 points. Let's pair it. Pair it into 2 groups. See, 1 and 2 together, 3 and 4 together. This is one way to pair them. Okay. The second way to pair them is 1, 3 together, 2, 4 together. Okay. And the last one is 1, 4 together, 2, 3 together. But the point is, whenever you pair them, that's the construct a df function. Okay? And df is a Feynman propagator. That's what we learned. df is just the 2 points with time ordering. Okay? 2 points with time ordering, we call it df. Or if I have many, many points, the result turns out to be you have to pair them. Okay? Pair them. Is that clear? This is very intuitive, right? The first is I have 1, for instance, this is my 1, 2, this is 1, 2, 3, 4. So the first pairing is 1 and 2, 3 and 4. Okay? Is that clear? The second is 1 and 3, 2 and 4. The second pairing is like this. Okay? And the last one is the 1, 4. And 2, 3. Okay. It's very simple, right? It means what? It means whenever I give you an even number of whenever I ask you to compute this even number of correlation functions, when n is even, okay? Even means compare it over, okay? Then you can immediately write down the results. You don't need to calculate. According to Wick's theorem, you don't need to calculate. You just pair them and then write down the result. Okay? Each pairing contributes a term and sum them together. For each pairing, this pair, each pair contribute a df, and you multiply this df. Okay, that's it. So of course, this Wick's theorem needs to be proved, which I skipped, and you should too. And in order to, but I can sketch the way to prove it. Right? So in order to prove this Wick's theorem, one can define something called normal ordering. Okay, normal ordering. Normal ordering, you know, we now learn the time ordering, normal ordering. Maybe you're just confused. What is order? Time ordering is already clear, right? We just if you hand me a bunch of operators, I just see which one is earlier, which one is later, and go by force to order it. Okay, I just put the later time one to the left. That's it. Now there is something called normal ordering. Normal ordering. Normal ordering means Because essentially those questions are related to how to calculate the AA Dagger. There are many AA Dagger, right? So each phi has an AA Dagger combination, right? So you put many higher point functions, you have many AA Dagger, okay? Then the normal ordering says that I always put the A or AP to the right and the A dagger to the left. Okay. Okay. Whenever you hand me which kind of A dagger combination, I by force shift the A operator to the right and the A dagger to the left. Okay. Then this is called normal ordering. And use this kind of, sometimes we using this fancy label to label this n. For example, we can use n, because T is time ordering, then n is long ordering, okay, with a bracket. And this can mean the long ordering. Sometimes when you write a textbook, sometimes people always write something inside and using this kind of points to label this long ordering. But that's just the same thing, okay? That's the same thing. I can put something inside and make this point, the meaning this for the given object inside. I do the normal order because that's just the same thing. So this normal ordering is good to prove the Wick theorem. So basically, Wick theorem can be stated in this way. This is the final result. This is not the precise form of Wick theorem. So let me state the Wick theorem. Wick theorem is that whenever you have a bunch of operators, the time ordering is related to normal order. And once you have Wick theorem, you can easily get that result, simple result. Wick theorem says that if I have phi1, phi2 up to phi n, I will think about the time ordering, and this is always given by the normal ordering of phi1, phi2, phi n, plus all possible contractions. This contraction is not necessarily to be contracted over, but just all possible. Let's imagine all the possible contractions. And one term for each. One term for each possible way. And not it will be to contract over. Now, if you accept this, theorem, then you can easily get the result, right? Because only for those contracted over terms, they become some number, okay? If they become some number, normal ordering doesn't mean anything. It's just a number. It's not an operator. Normal ordering means it's just for operators. Okay. But the point is, for any other pieces or terms, once you have a normal ordering, you cannot get a non-zero expectation value. Okay. Because A is always on the right. Okay. Is that clear? A is always on the right. A is always the first clear the vacuum. Okay. Then you always get zero. The point is, any non-trivial normal ordered operators contribute a zero result. Okay. Only for those contractions belong to all the possible contractions. There are some contracted over contractions. Okay. Only those terms contribute a number or constant. For those constant, it can pass through this n, right? It doesn't mean much. You do one order, then it becomes some non-zero result. That's it. Oh, of course, again, I skipped how to arrive here. I skipped the derivation, how to derive this result. Okay. You can try to prove it. But once you do that, you can easily get this result. Okay? Okay? So the result is very simple. You can check yourself for 6 points or 8 points. Now, you ask me, what about 3 points? How does this theorem work for 3 points? 3 is an odd number, cannot be paired over. What about 3 points? Can you guess the result for 3 points? Or 7 points? You get 0, essentially. Because there's no way to contract over. Then you get 0. Okay? You get 0. Because once you have 3 points, now 2 of them contract over, it becomes some number, right? Then what about the remaining one? When you have a number times some operator, you measure the expectation value, of course it's 0. It's a 1-point function. Only a 1-point function is 0 in these free fields. Right? Because phi has A and A dagger. A will kill this right vacuum, okay? A dagger will kill the left. You always get 0. So the 2-point function can be non-zero. And all the even point function can be non-zero. But all the number of functions is 0. You have any question about the Wick's theorem? The statement of Wick's theorem here, and the result coming from Wick's theorem here. It's very simple, right? Very simple.
这个大 N 它换顺序的时候，它把对义字加上去了吗？
No.
没有。
As time ordering, it's just by force.
Oh.
This operation really you do it by force. Okay. Whenever you give me something, I just reordering it. Okay. That's the definition. That's the definition. Now the small subtlety here is maybe you worry about something like this. If I have 2A, 1A dagger, okay, then you ask how this n normal ordering can give me a unique result if it's just into your example, into your ask. For example, then let's talk about the normal ordering or n's. Of this A P dagger. Well, so just as an example, okay. Now consider AP dagger plus AP times AK dagger plus AK, and then I want to do the normal ordering. What will happen? Okay, what happened? What will happen is, as I said, I always put the A in the right. Okay, so the first time A dagger is okay. No. And right, for this term, that's already normal order. I don't do anything. Now for this term, I have to do something, right? Because I have to switch this normal order for this term. Now the last term, I don't need to do anything. Okay. Now you may ask if I have more operators, in what sense this result is unique after normal order? The point is, when you have AA, you just commute. AA always commute. So no meaning for, it doesn't matter you switch, you put the AP, AK or AKAP, because AP, AK are always commute.
What about for fermions?
That's a good question. For fermions, you slightly change the. You can define this way, but as you know, the difference between the normal order result and the original result is some anti-commute, not a commute. Right, because when for fermions you switch the order, yeah, you differ by some anti-commute. So that's normal ordering, right? Normal ordering is also very simple. Normal ordering is also very simple. And now you can try to prove this one. So once you prove this, the result is very immediate. So we have 10 minutes. Do you have any questions? We have 10 minutes. Either we can go to the interacting theory, have a very short beginning within the next 10 minutes, or you want to ask some questions. I can respond to the question.
不一定，还是这个 all possible contractions，它到底含义是
just okay, very good. It's just
in the real
it doesn't mean, for example, this is one contraction. All the possible means I don't need to contract over. But I do need a contract. Contract means what? Okay, by the way, contract essentially means you pair to form a DF. That means contract. That's the definition of contract. That's the definition of contract. The Wick theorem says that this must be equal to this term. This term plus all the possible contractions. This is one contract. Means for this case, you have to add a term, make it a single term here. And then for other contractions, and all the possible ways, you have add plus. Then you realize that eventually, when you measure the expectation value, okay, of this right-hand side, only those terms contract over, okay, can contribute to the non-vanishing constant. All others is gone. Why? Because normal ordering. Normal ordering shifts the A by force to the very right hand side. Okay, very right hand side. Then this A must kill the vacuum. That's it.
What about the normal order？
Normal order.
就是 contract 出来不是就一个表吗？
如果这么说的话，那它和这个 normal ordering 有什么关系？
Normal order. Normal order is normal ordering. Sorry, maybe I didn't get the
就是如果说它这个 contract 出来就是一个 Riemann function， 那么它和这个 normal order 的表示有什么关系？
说是 time order， 这里就在
就是如果表示的话，它不就变成了那个样子吗？那个就是它收缩之后就会变成了
Yeah, this is contract over.
yes。
Yeah.
所以它和这个为什么要用这个 normal？
这不是
That's you have to go to the details how to prove it. Well, obviously, one reason is introduce the concept of normal ordering in order to let many terms trivial become trivial. Okay. But to prove this equality is non-trivial. With this. Any other question?
老师，就是我想问一下那个对子为什么跟那个因果性之间是有这样一个联系的？就是为什么对子等于零？就是说他们两个点之间没有这个因果的那种信息的传播和因果性。
后面一句没听清。
就是你这个说对子等于零，然后你就说他们两个点应该是没有那个因果关系的，或者说信息无法传播吗？ 那这个对子就是说怎么跟因果性就是说建立联系？我不太清楚这个。
Okay, that's a good question. Let me try to explain more details. One way to think about it is this way. Commutator can be viewed as how an excitation or how a measurement performed at one point affected another measurement. That's right. How a measurement performed at one point it can affect the measurement at another point. Then yeah, I don't think there's a very deep physical interpretation. I mean, just try to interpret the physical meaning of the commutators. But I think at this moment there's a beautiful, sharp physical mathematical fact, which is the commutator really corresponds to the orthogonality, meaning if this is zero, this is zero, this is not zero, this is not zero. Okay? Or commutator can be used to justify whether 2 points are causally related. But if you ask me how to interpret this correlator, you really want to using causal language to interpret these correlators. Yeah, I'm not sure there's a clear interpretation.
那如果
As a result,
就这个地方你是考虑两种情况，那如果说我们考虑 x 是 time like， 然后 y 是 space like， 那这个对子会是怎样的？
say it again, x and y.
就是 x 是 time like 的，然后 y 是 space like 的。那现在这个对子
No, you cannot talk about a single point as timeline or only 2 points.
对 x y 就必须得是同时是不是 space like 或者 time like。
No, okay, I understand your confusion. Don't confuse them. Now here, I'm saying the x, y, time like or space like, I mean the distance. You standing at the x point, observe y. Okay. But sometimes we also put x or y itself time like or space like. That means you standing in the origin. Okay. Origin. Then any points are the vectors. Okay. But that's not useful here. I don't care where the origin is. Here, I only care the relative position between x and y, right? I don't care the other origin. So you don't need to worry about that.
What if they are like?
Right, like good. That's a good question. So let's first say what is the mathematical result? What about the light like? Can you check it? If it's light like, what will happen? That's a good question. I leave you to think yourself. Okay. Any other questions? We still have 2 minutes. Yeah, we will leave the S matrix or interacting theory discussion to next time. So next time we're going to continue to discuss to go beyond the free theory. As you can see, we almost finished all the stuff for free theory today. We talk about 2 points, higher points, all different 2-point correlators using this for argument. But don't forget, these are all just for free field theory, which is very trivial, okay? Which is very trivial. The real interesting thing is the interacting theory, okay? Then what do you do? What can we do for interacting theory? Even how to define interacting theory, okay? Do you think about that? What do we mean by a theory is interacting? That's right. So in Lagrangian, we don't only will not only have these 5 square terms, but we have some higher power. For example, 5 cubic, 5 to 4. For example, we have something for the 5 4. Okay. If some coupling looks like this in my Lagrangian, then this is the interacting theory. Then an immediate challenge is not like the free case. For interacting theory, if you want to find remember that when we do quantization, we go 5 steps, right? 1, 2, 3, 4, 5. One key step is to find the solution for the classical equation motion. You have to find the solution and then quantize. But the point is, for such kind of theory, there's no such kind of solution, okay? You can try yourself. Write down the PD equation for such kind of theory. Then you realize that, oh, it's almost impossible to find a solution, a simple solution for the interacting theory. We have to do something else, okay? So straightforward quantization doesn't work. We have to do something else. So that's the topic of next time. Okay. Stop.
本来想几个意见很好，没来得及，我那个
真的是，这个不一样，这个读者自证不打对吧？应该是我操，
如果你有脾气嘛，别忘在那个放在图感，单调的，你是投的。
这个交换的方式，
然后也差不多那个物理上讲就是从物理上讲呢，就是说它那个物理上讲就是这个点，如果对比组半球，就是它对如果电池对方
对，一样的，这个就是你
相当于这个反正对，那歪的点可以。那已经太太歪了，那我很快对。对，不是发散，就是零啊，我要不然就零啊。
我这个
就是发散，就是极致轴联，
就强制排序嘛。但强制排序好像就没有说出不到。
是的。
关键是 ，whenever 你强制一个强制，就是当你发现这个位置的时候，你要交换。但是就是你 measure 这个，
或者说你 P 在翻译 fire 呢，或者是 fire 翻译，就这个出来就有可能插个括号。
你说对什么？
就是你如果是程序翻译，
对，
或者这个程序
你解释一遍说都，switch， 这个没有这个。手加的。这个手加是看着很方便，
这也像是一个技巧。
它如果不加会
就是不加的话，就需要用这样一个围道。
不加也没问题。
加了的话，
就要把围道画出来。
加了的话，这个围道就可以变成一条直线了。
哦，以为在这个道上还要再加。
不是，
这是一个
替代品。
把围道
用这个 trick 我就可以补这个符号，我就不用做任何控制，自动实现。啊？
收到流动作业。没有，那我得先搞清楚的。
所有可能
对，还有这个。它本来就是算，
因为
这有几个例子。
对啊，这有一项没有 contract 我不在的。
哦，所以所有 contract 意思是你带一个这样 contract，以及后面不带，或者带一个这样。
一定要带有一个。
对，它可以不用全 contract。
后面不是全 contract。
不是，而且如果这个是奇数的话，你后面会全 contract。
啊，对，我是这个意思。就是说，所有的 contract 不是说所有都要 contract 起来，而是说只要带 contract。
所以那个我只是 contract
但你做内梯的话，它其实就全部到。
可是你没有 contract 起来，你
这样就是你大概没有什么特别什么，这里面有 contract 但没有。
哦。
那做内梯，你不要 contract 这里。 那它那个已经
对吧？这是加
记住的话，两个都变成
没有这一项不完整，
基数的
因为它要让这个等号是。
对啊，因为
这个等号是个 operator 可以使用。
它没有全部，
它没有开始计算它的期望值，所以这个等号严格成立你不能随便跟项。只有 operator，就这里面只是 operator， 没有
一个那个监控期望。
用监控加的话，很多项都有零，但是要让这个 operator equation 非常准确，这里面不能随便跟。
监控项加它一定要全说并它才不为零。
对啊，
这
很显然，
这个上肯定要
对啊，因为很显然，因为我已经把它包了。
对啊，这是基数项的话。